Okay, so Coulomb's law is the basic law of electrostatics. We can use it to calculate the force a positive charge exerts on a nearby negative charge. But it leaves us with an unanswered question. How does a charge know that another charge is there? Coulomb's law tells us how to calculate the magnitude and direction of the force, but it doesn't tell us how the force is transmitted through empty space from one charge to the other. To answer this question, we'll introduce the idea of the electric field. By the end of Lesson C, which will be covered in 4 separate videos, you should be able to define the electric field in terms of the force on a test charge, describe and calculate the electric field of a single point charge, calculate the magnitude and direction of the electric field produced by 2 or more point charges, calculate the magnitude and direction of the force on a positive or negative charge placed in a specified field, interpret an electric field diagram, and analyze the motion of a particle of specified charge and mass in a uniform electric field. In this video, we will introduce the field model and look at 2 examples that utilize it. So here we go. So what do we mean by field? All the term field means is that there's an alteration of space around whatever it is we're talking about. We can talk about 3 types of fields: the gravitational field, the magnetic field, and the electric field. The gravitational field is the alteration of space around a mass. The electric field is an alteration of space around a charge, and the magnetic field is the alteration of space around a magnet. In the field model, it is this alteration of space around an object that is the agent of a force on another object. For example, the Earth is surrounded by a gravity field. Any object with mass will have a force exerted on it by Earth's gravity, and it will exert an equal force on the Earth. This is fairly simple to picture in your mind. You have the Earth pulling down on things with the force of gravity, but because the force of gravity is so weak, we don't have to worry about the force of gravity between objects that are in Earth's gravity field. This is not true for electric charges. If you have a group of electric charges, the forces that they exert on each other are significant and we can't ignore them. It would be like having 3 or 4 planets scattered around a volume 1,000 times smaller than the solar system. They would all exert tremendously large forces on each other. Because of this, we have to treat electric forces between charges way different than we treat gravitational forces between masses. So we'll begin our investigation of the electric field by establishing a model that we can use to describe how 2 charges interact. This model can then be used to describe how any number of charges will interact. So first, let's recognize that in any situation, we will have source charges that alter the space around them by creating an electric field. Second, any other charges that enter that field will experience a force. The agent of that force is the field set up by the source charge. Third, we measure the strength of the electric field in terms of the force on a probe charge placed within the field. No, sometimes we call it a test charge, sometimes we call it a probe charge, but we're going to measure the strength of that electric field in terms of the force that's placed on some test charge. And finally, the electric field is a vector, and the net electric field is the vector sum of the individual fields set up by multiple charges. So this is our field model. To gain a better understanding of our field model, let's apply it to a gravitational field, something that we have a little bit more experience with. Now, the Earth has a gravitational field we experience every day. So the Earth is like our source charge. It sets up the gravitational field. Any mass that's brought within the field experiences a force, right? So if we say that you are the mass, then you experience a force on Earth, and the agent of that force is Earth's gravitational field. If we want to describe the strength of that force, we describe it in terms of the force on you. If we take you to a different gravitational field, say to the moon, then you will experience a different force due to it being a different gravitational field, right? So in the same way, charges in electric fields will experience forces. So the electric field is a way of describing how a point charge or several charges influences the space around them. The electric field at various points around a charge distribution can be analyzed by measuring the force of the distribution creates on a test charge. So when we describe the electric field, we do so from the perspective of a small positive test charge placed within that field. So the electric field, which is abbreviated with the letter E, is a vector quantity. It has both magnitude and direction. The direction of that field is in the same direction of a force on a test charge within that field. This test charge is always considered to be a small positive charge, and it's assumed that the test charge does not disturb the charge distribution or create a significant field of its own. So in these drawings, big Q represents the charge causing the field, the source charge, and little q represents the small test charge. So in this first case, big Q is positive and the test charge is positive. So the charge, big Q, alters the space around it, and the test charge, little q, responds to it. If we move it to a different location, the force exerted on it will have a new direction, but it's still going to be away from the source charge. And if we move it closer, that size of that force will increase. So now let's take a look at how we can quantify the strength of the electric field. So the electric field strength is a measure of the strength of the electric field. We represent it by this symbol E. Here, E then represents the field intensity. F represents the force in newtons acting on a test charge Q. This charge is not the charge that has set up the field. This Q is a test charge that is in the field made by some other charge, the source charge. This is an important distinction that we need to make, and the reason for this distinction will come clear later. For now, you can think of the Q in this equation as like the mass in the weight equation for gravitational fields, the W equals mg. Now, the units for electric field are in newtons per coulomb. Now, the basic idea of the field model is that the field is the agent that exerts an electric force on charge Q. But there are three important things about this electric field, some of which we've already mentioned, but I'll mention them again. The electric field is a vector, exists at every point in space. So we'll make electric field diagrams, and they'll show a sample of the vectors, but there's an electric field vector at every point, whether one is shown or not. And here is an example of an electric field diagram. Second, the probe charge, Q, is positive. So the electric field vector points in the same direction as the force on that test charge. If the source charge is also positive, then the electric field points away from the source charge. If it's negative, the field points toward it. Now, because little q, the probe charge, appears in this equation, it might seem like the electric field depends on the size of the test charge, but it doesn't. Now, we know from Coulomb's law that the force on Q, on that test charge, is proportional to Q. Therefore, the electric field in this definition is independent of the charge that probes the field. The electric field depends only on the source charges that create the field. To make more sense of this, think about a gravitational field. When we put an object into Earth's gravitational field, does that object affect Earth's gravitational field? Well, no, it doesn't. So the same is true for an electric field. You are in Earth's gravitational field. You don't affect Earth's gravitational field. So in this same way, the test charge does not affect the electric field. So let's take a look at a couple of example problems. So here we'll start with a pretty simple example of this electric field equation. We have an electric field with a field intensity of 2.5 times 10 to the 4 newtons per coulomb. The force acting on a test charge is 7.4 newtons. We want to know the magnitude of the test charge. This is a pretty simple example of using this equation. And we end up with a charge of 2.96 times 10 to the negative 4 coulombs. Okay? So let's take a look at an example that's a little bit more involved. Okay, so here we have an electron traveling along at 2.3 times 10 to the 5 meters per second, where the direction is shown in this drawing, and it enters a uniform 280 Newton per coulomb electric field. We want to analyzing the electric lines of force, we want to figure out the direction of the force acting on that particle. What is the magnitude of that force? What is the acceleration acting on the electron? And if that electron travels a distance of 3 millimeters in the field, what's the distance it will be deflected from its original path? So to solve this, let's imagine this were a ball being thrown into a gravitational field. So instead of this being an electric field, we'll pretend it's a gravitational field, and this is a ball. Now we throw a ball into a gravitational field, and it's going to be deflected, and it's going to land down here somewhere. We can look at this problem in the same way as we would a ball going into a gravitational field. It's just kind of like a projectile motion problem. So we start with part A, analyzing the electric lines of force. What's the direction of the force acting on the particle? So these electric field lines, or electric lines of force, they point in the direction that the force on a positive chest charge would go, okay? But this is an electron being shot into this electric field. If these arrows are pointing in the direction that the force on a positive charge would go, this is a negative charge, therefore the force on this negative charge has to be in the opposite direction of these electric lines of force, or these electric field lines. So for part A, because this is an electron, our force on this electron is down. Okay, great. So part B asks us to figure out the magnitude of that force. Well, we're given information about the size of that electric field, so we can figure out easily the size of that force using our electric field equation. So we're told the size of the electric field is 280 newtons per coulomb. We're looking for the force. We would find the charge of an electron from our table of information on our equation sheet, and that's 1.6 times 10 to the negative 19 coulombs, giving us a force then 4.5 times 10 to the negative 17 newtons. Okay, so part C asks us to figure out the size of the acceleration on this electron. Well, this electron is being shot into this electric field, and as we talked about in the previous video, the size of a gravitational force versus an electric force is so much smaller. We can pretty much ignore the effect of gravity on this electron, and so the only force acting on the electron is the electrostatic force from that electric field. So we can use simple F equals ma to figure out the acceleration. And again, we look to our equation sheet, a table of information, to find the mass of an electron to be 9.11 times 10 to the negative 31, and we end up with an acceleration of 4.92 times 10 to the 13 meters per second squared. There's our acceleration of our electron. Now for part D, we have to, think a little bit more about this situation, okay? So here's another picture of it then. So here's our electron when it enters our electric field. We know it's deflected downward because it's an electron. Electrons are going to be deflected in the direction opposite the electric field. And we're told that this electron goes 3 millimeters into that field. So we want to know the distance it will be deflected from its original path. So what we're asking for is, here's its original path, right? We're asking, what is this right here, this distance? So this is like asking what the height of a table is when we've launched a ball horizontally off of it. The horizontal velocity is constant. The acceleration is all vertical. So first we have to find the time down and then find y, the distance. So thinking about this problem like a projectile motion problem makes it a whole lot easier to deal with. So to find the time down, or to the time it takes to be deflected to the bottom of this electric field, we're just going to use our constant velocity equation, and we're given initially the velocity in that x direction, which is going to be, just like for a ball in a magnetic field, it's going to be independent of the vertical velocity. And we put in all our values, and we end up with a time down of 1.3 times 10 to the negative 8 seconds. Well, great. Then the only thing that we have to do is apply kinematics to figure out the distance, the y distance. So that involves using this second kinematics equation, and we end up with a distance of 0.0041 meters, or 4.1 millimeters. Okay, so this is an example really utilizing that last bullet of our learning targets. Make sure that you go through it enough times to make sure you kind of understand what has been presented here, and that you understand the concepts behind it. And these two examples are examples of what happens to a charge in an electric field. We don't really know anything about the charges that set up the fields, the source charges, only that those fields exist. In the next video, we'll begin to learn about how to describe the electric field when we do know something about only the source charge itself and not anything about test charges. See you then.